In part 7, I showed you how to make particles chase after a locator. But suppose that you want each particle to chase its own target and to settle thereupon when it reaches it. In this video, I'm going to attempt the improbable. I will try to make Steve attractive. I will make blobs chase the blob chaser. Instead of a locator, we will use points as targets. So, without further ado, I'll use the text tool to create a target shape. And I can use the particle paint tool to apply some points. Try and get a reasonably even coverage, and I'll skip the video ahead so that you don't have to watch me painfully applying these points. There we go, and let's just rename the mesh to something sensible. And we can get rid of the text itself because we don't need that anymore, or when it's done its job. All we need now are these points, which will be the target for our particle system. I'll also need a particle source. Let's stay simple and just use a radial emitter. And let's put that somewhere useful and set up its cone angle. Let's wind that down. Rotate the radial emitter. And position it above the text. So it's going to squirt particles down towards the text, and the particles will be attracted to these points. Let's animate the emission rate of the radial emitter so that we have a big burst of particles at the start of time, and then that tails off rapidly. So at time 0 we'll have, say, 5,000. And then at time 5, let's go down to 0. If we play the simulation, we should see a big burst of particles coming out. Right, one last thing. Let's bring these things into the schematic. And while we're here, we might as well add the blobs that we're going to be using as our particles. So let's add a blob and wind its size down to something reasonable. Drag the blob into the schematic and use the particle simulation as the particle source for the blob. Now we should get blobs coming out rather than just point particles. Now we may need to adjust some of these settings later on. Those might be a bit too big, but let's see how it goes. As in the previous video, we will need to add a particle operator. This will be the engine that will drive the particles towards the point targets. So let's add our particle operator. Okay, being incompetent, here we go. Right, let's get rid of these two because we're not going to use them. Remove channel from node, and we're going to need to add some features to this particle operator. Well, we're going to need to add a force, because a force is what's going to be used to drive the particles towards their targets. So let's add particle feature force. We will also need to know where the particles are. So let's add particle feature position. We only need to read that. And another thing that I'm going to add is the particle ID. Now the reason for this will become apparent later on, but for now just trust me and you'll have to remain in suspense as to what on earth the particle ID is for. Let's separate out the read-only features so that we can move them to the other side of the diagram and keep things tidy. I'm a stickler for tidy diagrams. There we go. So the big question is what goes in this big gap here? We need to calculate a force based on the position of each particle, well that we get from the particle operator, and on the positions of the target points. Now fortunately there's a geometry constraint that allows us to do just that. It's called geometry constraint position. So let's add that constraint in. We will need to supply a number of inputs to the geometry constraint, including the mesh that we want to constrain to and the transform for that mesh. So let's do that first. Let's bring Steve into the schematic and add some channels. We'll need to add the world position, rotation and scale. Drag those in. And we will also need to add the mesh channel. So connecting up the mesh is straightforward. We just connect it up. Comme ça. But the transformation is a little bit more complicated because we've got three transformations here. We might be positioning, rotating and scaling our target, and we need to combine those into a single world transformation which we have to feed into this constraint. Well, from the previous video we've seen exactly the tool we need to do that. It's called Matrix Compose. So let's combine the transformations using Matrix Compose and feed the combined transformation into the constraint. Like some digital dating agency, we need to decide which point each particle is attracted to. This is where the particle ID comes in. The constraint has a channel imaginatively called index A. Let's add that in. This channel selects the vertex that we're interested in. It's just a number from 1 to the number of vertices in the item. And we can find out how many vertices there are by going to the Lists tab and looking at the number of vertices. So we have 881 vertices. That's going to be important because to select the vertex that each particle is interested in, we're going to use this particle ID to control the index. Now the index goes from 1 up to 881. The particle ID, on the other hand, is just a number from 0 to 1. So we need to convert 0 to 1 to the range 1 to 881. And the easiest way of doing that is to multiply. So we'll add a math multiply, feed in the particle ID, put that into index A, and the scale factor is 881. So now for each particle we will generate a number which goes into index A. It picks out one of the points from the mesh and gives us the transform for that point. we can turn that transform into a position, and then we can subtract the position of the particle from the position of the point that it's headed to. That should give us a vector which we can then scale to feed into the force, and we should then get our particles heading towards their target points. So let's do that. First, let's turn the transform output into a position. We need to add a matrix vector which turns our transform output into an XYZ vector. We don't want the X, Y or Z rows of the matrix, we want the translation row. I always uncheck normalize. I don't think it actually matters, but if weird things happen to you, that might be something to look at. Next up, we need to take the position of our particle and subtract that from the position of the point that we've just established. Let's make a bit more room in the diagram. We need a vector subtract. And remember, if we get this the wrong way round, we can always flip the sign of the force. And we need to scale this vector, otherwise the force is going to be much too strong. These diagrams get very wide very quickly. Let's add vector set length. So the vector in, and let's bring the length channel into the schematic so that we can edit it directly, and feed the output into the force. And let's change the length to something quite small, like 0.01. And let's see what happens. Oh dear, it's the wrong way around. Let's change the sign of the length. Well, okay, they're being attracted to Steve, as opposed to earlier when Steve was repulsive. But they're getting a bit excited. Well, we know a way to stop all that sort of excitement. We can change the drag force to slow particles down a bit. Let's try 10. There we go. The particles now coalescing around their target points. But we have a problem. They're not settling. Like some hyperactive child, they can't stay put. And let's see what we can do about that next. You probably nodded off by now, so you probably didn't notice me rearranging this diagram to make it rather neater. Okay, so I sneakily did it whilst you weren't watching. What I've also done is I've given the particle operator an editor colour. I find this useful when I've split off channels from an object so that there's a visual cue to tell me that all of these red objects are in fact the same node effectively. So, how to address the jiggles? Well, we don't have any Ritalin to hand, so we're going to have to use something else. What do we need to do? Well, the particles are sort of oscillating around their targets and never actually reaching the target point. What we can do is check to see whether the particles are within a certain threshold of the target point, and if they are, set their velocity to 0. That will stop them jiggling in their tracks. However, what do we do for particles that aren't quite at their targets or aren't anywhere near their targets? Well, in that case, we need to set the velocity to what it is already, i.e. we just set the velocity to the current velocity, and that should make no difference to the particle's behaviour. So let's try and do that. First off, we're going to have to add the velocity as a particle feature, and we'll need both read and write. So let's add velocity and velocity read only. And separate those out. I'm going to use an assembly which I've put together which lets me select between one vector and another. So the point of this assembly is that you pass in two vectors, vector A and vector B, and you set this select input to false if you want to select vector A and to true if you want to select vector B. So the easy bit is wiring up the output. We'll stick that into the velocity. The idea is that most of the time, as the particles head towards their targets, we will just set the velocity to itself. So we'll read the velocity, it'll go into vector A and come out in the output and appear as the velocity to be written into the particle operator again. That will make no change to the velocity. But when we get within a certain distance of our target points, we want to set the velocity to 0. So if I don't feed anything into vector B, that will be 0 by default. But what I do need to do is work out when select B should be true. And that we need to do from the distance of the particle from its target point. Unfortunately, we've already calculated that in this subtract node. That's what the value output x, y, z here is. It's the distance between the, or at least it's the vector between the 2 points, the particle's position and its target point's position. To turn that into a magnitude or a distance, we can use the vector magnitude operator. Feed the x, y and z into there. Let's move that over a bit. So if the magnitude is within a certain threshold amount, we will select B. So we need a conditional. So if A is less than B, so if the magnitude is less than some threshold value, let's try 0.1 to start with, then we will be setting the velocity to 0. And let's see what happens now. Perfect. I wasn't expecting that to work first time, but it has to happen sometimes, I suppose. Let's bake the animation. And let's see what it looks like in render. Okay, well I think those blobs are probably just a bit on the large side, so let's go back to the blob and change the size. Well, you get the idea. So all would appear to be well in Jumanji, But what happens if we animate the item? As you can see, the particles get detached from the targets and then have to reseek. Now this may be the effect that you're looking for, but possibly what you would prefer to happen would be that the particles, once they've reached their target points, stick there and hang on for grim death. And this is what this second scene is all about. So what's the difference between this second scene and the first scene? Well, the main difference is that rather than setting the velocity, we are now setting the position. So how does this work differently? We use this vector select assembly to choose between the original particle's position and the position of its target point. So when the particle is flying free, we set it to the position of the particle, and that means that the particle position will be unchanged from what it was before. But when the particle is stuck, we set it to the target point's position. How do we make that selection? Well, this is the tricky bit, and that's what this part of the graph at the top here does. I've hijacked this feature, collision count, to keep track of whether or not the particle has stuck. So initially the collision count will be 0, or you can think of that as false. So false will come into this OR operator and be ORed with this condition here, which is the thing that detects whether or not the particle has got within a certain threshold of its target. So initially both of these two will be false because we won't be near the target, and the particle operator collision count starts off at 0. So we get false coming through here, so B is not selected, so we set the particle to its original position. What happens when we reach the target position? At that point, this test here, A less than B, the distance of the particle from its target will be less than this threshold value, so this will become true. It will go into the OR, true or false is true, so the true will select the position of the target point. What's more, this true will also be written into the collision count, so the collision count becomes 1 or true. Next time round, collision count will be read back as true, and so regardless of whether or not the particle is close or to the target point, we will get true coming out of this OR operator. So this is sort of like a sticky effect. The collision count, once it gets set to true, will forevermore be set to true again. So once the particle has got within the threshold value, this sticky value, the collision count, will be set to 1, and we will always be selecting the target point position into the position of the particle, and so it will stick to the target. So that's a very quick rundown on that new graph. I'll make both of these available for download. I think that just about wraps it up for this video. I hope it was useful, and I'll see you in the next video.